move on to the last podium presentation of today of environment and material. And let's welcome Anna.
Okay, all right. Thank you so much for all the patience with my technical problems, and I'm super happy to be presenting today. I'll be presenting on air quality changes in COVID-19. More specifically, I'll be exploring the relationship between NO2 pollution and COVID-19 related closures. This project was supervised by Professor Greg Evans and Dr. John from SOCAR. So, first of all, I would like to talk a little bit about nitrogen dioxide pollution. Nitrogen dioxide pollution belongs to a larger group of nitrogen oxides, which is commonly known as NOx. It's a very, very common pollutant in the atmosphere, and it's also used as a key traffic marker since it's commonly found in diesel exhaust. Since COVID-19 related closures caused a large reduction in traffic, many people are also saying, well, this should cause a reduction in NO2 as well. And this is the larger problem that I would try to be analyzing today. So why should we care about NO2? Well, nitrogen dioxide, like all of the other air pollutants, have a lot of impacts on human health. For example, it's known to increase the cardiovascular mortality, respiratory mortality, as well as to cause premature childbirth. By analyzing this relationship between a reduction of NO2 and human activity, or in this case, traffic, we can evaluate some of our current methods used to reduce nitrogen dioxide, as well as coming up with new directions to look into for air quality improvement. This, of course, is very important for the benefits of overall human health. So, of course, I can't say that nitrogen dioxide had any reductions without giving something to compare it to. And therefore, I decided to display how nitrogen dioxide changed in 2020. The graph here shows the nitrogen dioxide from 2015 to 2018 displayed by the blue line, and then the green line displays the average nitrogen dioxide for 2020. This orange line indicates when Ontario started its state of emergency. So naturally, that's also the point where you would expect a large reduction in traffic. And you can see that the nitrogen dioxide for 2020 is a lot lower than the past year averages. As a matter of fact, there was a 35% reduction observed in 2020, especially after the closures. Now, many would say that this would solve the problem, right? There was a reduction in nitrogen dioxide, there was also a reduction in traffic, and therefore, it must be the cause. However, unfortunately, that's not as simple as I wish the question could be, since nitrogen dioxide as an air pollutant is highly variable. It has many temporal variations. For example, it has daily patterns, it has differences between its weekday and weekend values, and these are summed up by time variations. These are a little bit easier to deal with, as I can take the average over a longer time span, say for example a week, and mitigate the variations. However, there are also seasonal differences, which are a little bit more difficult to deal with. These seasonal differences can be summarized as a combination of meteorological influence. So, for example, temperature, wind speed, solar irradiance, the humidity or precipitation, and the boundary layer depth, which is reflected in a measurement of pressure. All of these variables will affect nitrogen dioxide concentration as it influences the removal rate as well as the measurements associated to nitrogen dioxide. And so to grasp all of these is very difficult. And therefore, the question I need to answer is, are the observed 2020 nitrogen dioxide reductions expected based on the given weather? And if it's not expected, then how much of this reduction can be attributed to other sources? To answer this question, I first need to define what an expected nitrogen dioxide trend is. In doing so, I decided to model nitrogen dioxide from a combination of weather variables. I built the model by using past data, so data from 2015 to 2018, and then using this model, I was able to input the 2020 weather data and predict what the values should be in 2020. After obtaining this, I can make a comparison with the predicted results and what's actually measured. And by comparing the two, I can get a sense of how much of a difference there is and do further analysis on that. So the model I used both a multiple linear regression and a machine learning neural network. For the modeling process, I did a lot of data pre-processing and cleaning. And after a very, very long variable selection process, I was determined to use temperature, wind speed, humidity, and precipitation to model nitrogen dioxide. I first explored a multiple linear regression model, and this is a model that offers a simple linear prediction. It's very simple and it's very straightforward in its dependencies. It's also very computationally cheap. However, as given by the name, it doesn't capture any nonlinear dependencies. So to explore the nonlinear dependencies, I also tried machine learning with the use of a fully connected neural network. This allows for nonlinear predictions. However, it is also a little bit harder to interpret as there isn't a coefficient associated to each variable. As a result, I obtained an R-squared of 0.61 for both of my models. Therefore, I decided to display multiple linear regression as my final model since it's a lot more easier to interpret and understand. This is a brief graph showing the model performance. As you can see, it's not a perfect fit. However, the R-squared of 0.61 does show a very strong correlation, and all of the points do satisfy the linear relationship between the measured and the predicted. So after I facilitated that my model was statistically significant and a pretty good fit for prediction, I could move on to predicting the actual 2020 averages. And this can be shown here on the figure in the bottom left. As a result, the measured NO2 displayed an average 36% decrease from what the predicted values should be. You can see that the predicted averages can be displayed by the blue bar here with around 15 as what they expected to be. However, we only measured around 9 ppb of NO2 during the months March to June. This can also be shown in the figure on the bottom right. As you can see, the predicted blue line is consistently hovering over the measured NO2, and it's not just from a lot of noise and a lot of oscillations. However, just a visual confirmation wasn't enough for me, and I wanted to further confirm that there was a significant enough difference for it to be abnormal and just a combination of a lot of model noise. So I decided to construct a 95% confidence interval. This is shown here. A 95% confidence interval is a range where 95% of the data should fall in. And by analyzing the differences, you can see how good two pairs of data can fit. You can see for 2015 and 2018, the predicted nitrogen dioxide had a confidence interval similar to the measured, all around 15.6 to 14.7. This is more or less consistent with the predicted averages for 2020 as well, as we predicted 15.7 to 13.8. However, the actual measured NO2 values were 10.6 to 8.2 ppb, which does not even remotely overlap with the ranges. This shows that there is a very significant difference, and something should be abnormal about how low it is. As a conclusion, when you're looking at the 2020 NO2 in Toronto, it is 36% lower than what the predicted values should be based on a lot of weather variables, and it's also 35% lower than all of the averages from 2015 to 2018. Therefore, we can draw the conclusion that there was indeed a very abnormal reduction. And this reduction should not be related to meteorological or weather influence, as it was still much lower than what the prediction based on weather was. Therefore, we know that we can move on to some non-weather variables, and the suspected COVID-19 traffic reduction is more than a valid option to explain this variance. After understanding this, we can think that now for controlling NO2 pollution in Toronto, methods of reducing traffic or reducing traffic emissions, such as just general traffic restriction and exhaust improvement, are both valid methods to explore and should have an effect. For future steps, I will be addressing some of the things that my model fails to address. For now, for example, NO2 actually experiences annual reductions. It's been on a gradual reducing trend for the past 3 decades, and that will be something that I will try to make the model account for that. Additionally, I would like to explore more geographical variations so that I can create a more generic model, as now my model is based on only Toronto data, and I want to see how widely applicable this is. These are some of the references I've used. And I would like to extend a special thanks to Professor Greg Evans, Dr. John, all of the lovely members of SOCAR, as well as Professor College for answering a lot of my questions and helping me with this project. Thank you all for listening. That concludes my presentation, and I'll be happy to take any questions.
Thank you, Anna. So the judges, do you guys have any questions? If so, please unmute yourself and ask.
Sure, I can ask a question. This is Glenn Hibbard. Nice presentation. Anna, can you talk a little bit more about the connection to weather? And what's the mechanism, how that relationship between how the NO2 levels and weather work, exactly how that kind of goes in? Can you talk about that a bit more?
Yeah, of course. The dependencies were very complicated for each variable, so I'm just going to briefly talk on it. Can you see the slide now?
Yep.
So for the meteorological influences, the connection of NO2 with weather is that a lot of things influence the reaction rates of NO2 production or like consumption in the atmosphere. So for example, the temperature and solar irradiance and humidity, these are things that influence the chemical reaction rates, and they will influence the levels of NO2 at a certain point in the year. So if you have a specifically hot summer, usually you should see a lower NO2. Some of the other variables, such as the wind speed and precipitation, these are influencing the physical removal mechanisms of NO2. So if you have higher wind speed, or if you're on a rainy day, you should naturally observe less NO2 in the atmosphere. The last one is a little bit trickier since NO2 is measured inherently as a concentration. The pressure and the boundary layer depth, which essentially restricts the volume of NO2, also will affect that reading as well. So these are some of the correlations.
And which of those, which is the most significant, do you think?
Through my modeling process, temperature showed to be the most significant because it had a very similar trend to the NO2. Among the others, solar irradiance and wind speed are also pretty significant. There was less of a significant observed for precipitation.
Okay, thank you.
Thank you, Anna, for your presentation.